Welcome to the binomial expansion extended. So on this page, this is the original binomial expansion that we studied. It's a plus b all to the power n, and then it expands it basically as in terms of powers of b or as a, and we see that we get these NCR things coming out of it. These are the numbers in Pascal's triangle. They are related to factorials as shown here. Actually, they come up in lots of different places, but here they are in this binomial expansion. Now, this is only true when n is a natural number. That means 0, 1, 2, 3, 4, 5, and so on. So when I say binomial expansion extended, I'm going to be pushing this on. I'm going to now be letting n be a negative number or a fraction or a negative fraction. Those are going to be the three that we really look at, and we're going to be able to get a formula a bit like this. What we're going to do is we're going to say, right, I want to expand 1 plus x to the n. Now n is some rational number. It could actually be irrational. Could be any number now, basically, a real number. And we're going to expand it as this series, a plus bx plus cx squared, and so on. That seemed to work over here. It's just here my series stopped, but I'm just going to assume for now on it just keeps going up, because I don't know what n is. And I can see that this is going up in powers of b. Every time the power is increasing by 1, so I'm going to assume the same here. And what I'm going to try and do is just see if it works. Use a bit of maths and see where we can get to. The first thing we can do, because I've got one equation with lots of unknowns, is I can maybe substitute in a value that makes life easier. If I substitute in 3, I'm going to get loads of coefficients on the right hand side, but if I substitute in x equals 0, then what I get on the left hand side is just 1 to the power of n, which is 1, and on the right hand side I just get a, because all these other ones will just disappear. So I've managed to work out that if this is possible, a is equal to 1. Okay, this is where a little trick comes in, and you're going to have to trust me with this. We're going to prove it later on, but if you differentiate 1 plus x to the power of n, then in a that should have a closed bracket. In a similar way to differentiating x to the n, you bring the power down and you reduce the power by 1. Actually, the same thing happens here. I promise we will prove this later on. For now, although it might be a bit frustrating, we're just going to assume that this result is true. Right, let's use it. Okay, if we do it to the left hand side, then what we get is, so basically we're going to differentiate both sides. Differentiate both sides. I'm going to abbreviate here. So then we're going to bring the n down. We're going to have 1 plus x all to the n minus 1. And now we're going to differentiate the right hand side term by term. The a disappears, the bx becomes b, the cx becomes 2cx, the dx cubed will become 3dx squared. The next one will be 4ex cubed, and it will proceed in a similar sort of way. Okay, and then let's do the same thing. Let's let x equal 0 in this. Then what's going to happen? Well, this is just going to become 1 to the power of n minus 1, which is 1. So we're going to get that n on the left-hand side is equal to b. And I've managed to get my first coefficient as 1 and my second coefficient as n. Brilliant. Okay, we're going to carry on. Let's differentiate it again. This time, so sorry, I'm trying to use a different color here. Differentiate again. So this thing in blue now I'm going to differentiate. I'm going to bring the power down. Remember, this is a constant n. It's only x that is a variable and that's changing. So I'm going to bring the power down. I'm going to write 1 plus x. I'm going to lower the power. And then I'm going to differentiate the right hand side again. It's going to become 2c plus 3 times 2. Check this out. I'm going to write this as 3 factorial. Okay, we're going to try and be concise with our notation. And then I've got D. And then I've got, okay, this one's not going to quite work. I've got 4 times 3x squared. By the way, I forgot the x here. Sorry, so I'm differentiating 2c to give c. I'm differentiating 3dx squared to give 3 times 2x, which I've written, sorry, dx, which I've written as 3 factorial dx. And then I've got 3 times 4ex squared. And we're going to substitute in x equals 0. And what are we going to get? Well, these terms on the right are going to disappear apart from 2c. This is going to be 1 again. So what I'm going to get is that I've got n minus 1 is equal to 2c, and c is going to equal n minus 1 over 2. Okay, we're going to do it one more time. You might want to pause the video and try it yourself. It's getting more complicated, but it's the same idea every time. Sorry, I'm differentiating again. N minus 1, n minus 2, 1 plus x to the n minus 3 will equal, now I'll be left with 3 factorial d plus, when I times by 2, I'm going to get 4 factorial ex. I've just realized I forgot an e here as well. Okay, apologies. That e should be there when I differentiate it through. And then I'll get some more terms. Okay, and that's going to mean when I let x equal 0, and this is the last one I'm going to do. When x equals 0, this one's going to disappear. All of these are going to disappear. This is going to become 1. So I'm going to get that d is equal to n minus 1, n minus 2 divided by 3 factorial. That's why I wrote it as 3 factorial rather than just 3 times 2, because you can sort of see a pattern occurring, perhaps. And so a challenge, I suppose, for you right now, what do you think E would be? How do you think the pattern would carry on? Have a little go at that. Just pause the video and have a go. Well, it turns out, and you can try this yourself, if you wanted to differentiate it again and then substitute in, that E is going to be n minus 1, n minus 2, n minus 3, sorry, that's being multiplied, I've just run out of space, divided by 4 factorial. And it proceeds in that kind of way. And we've sort of, I don't think you can quite call this a proof, but we've basically got the binomial expansion. By the way, this technique we've used is technically called a Maclaurin series. And if you're studying further maths, you will do this in more depth. But it's a way of getting a series from some function on the left that's like quite complicated, and you can do it for other functions as well. You can do it for sine, cos, and so on, and we will look into some of those. Okay, and what we actually get is, I've already mentioned this one. So first person to do this was Isaac Newton. He generalized, and this is the formula. Okay, so you have 1. So because once I've got my A, I've just put it into the formula. Once I've got my B, I put it in as n, and so on. Once I've got my C, I can write it, and I can generalize it, and I can just keep going. And this is what happens in general. For the power to be r, you just keep multiplying until you get n minus r plus 1. Let's just look at that. So for D, I had the cubic power, so that means I go up to n minus 2. Okay, for E, it was the 4th power, so I divide by 4 factorial, but I just go up to n minus 3. That's what this term, that's what this term here is saying in general. Okay, and actually it's an infinite series. It will go on forever. Right, I've got 2 or 3 comments now. The first comment is, how did Newton actually come up with this? I don't know, because Maclaurin series hadn't been invented when he did it, so not actually sure how he came across it, to be honest. But it does work, and it is true for n is negative or a fraction of both. It's actually true for n being an irrational number. We've got here that n is any real number. Second point, it only works if the modulus of x is less than 1. Now we will do more on what that modulus bit means. In this case, it actually means that x is between -1 and 1. Now, we're not going to prove that. Actually, to be honest, I don't know how to prove that. So I can see why it doesn't work for x that is greater than 1, because if you think about it, we've got this series that is infinitely long, and so x is going to get bigger. Like if x is 2, for example, then the sequence could potentially just get bigger and bigger and diverge, in fact. Whereas if x is less than 1, it will converge to something. I suppose I haven't quite proven that, but you can maybe get a feel for the fact that that will potentially happen. So that's something to be aware of. So actually, right, this is in the formula book. So you just need to be able to apply it, but I've tried to show you where it's come from. And actually, the main thing I think is really nice about this proof is that you sort of see where the factorial comes from. It's a bit strange when you first of all do the binomial theorem and you get these factorials involved, but it's kind of linked to this differentiation, the fact that we're differentiating lots of times, and that's why we end up dividing by 3 factorial, or in general r factorial. So that's really nice, I think. You're also told that it's just true for these values, and you will be tested on that. So make sure you don't forget about that. So please make a note of this. If you don't want to make a note of the proof, you don't have to. But not the proof, us basically roughly getting the formula. But please make a note of this. Now, third comment. Why this? Why have 1 here and not a plus x to the n? It's a good question. Because it doesn't get loads more complicated, I don't think, if you put a there instead. And you might want to experiment and see what you get for that. Now we're going to be able to deal with it just using this formula, and we get given this in the formula book. And the syllabus just sort of says learn how to use this one. You will be able to use ones with like a 2 in there or something. We'll talk about how, but this is why I've done it the way I have, because we've got the one that's in the formula book, so you can always refer back to it. Okay, that was a little introduction into the binomial expansion extended. This is the formula. We've shown where it comes from. We've talked a bit about the history. Now we're going to look at applying it to some questions. But to be honest, it's going to be very similar to how we apply the binomial expansion when n is just a counting number. It's the same sort of questions with maybe a little twist on it. But if you've got a good understanding of the binomial theorem, you are ready for this. Let's do some examples. The first example I'm going to do actually is when n is a counting number. So I could use my binomial theorem from before, but I'm going to apply our new one. So what we have here is the fact that n is equal to 3. And then I can write down that 1 plus x cubed is equal, and all I'm going to do now is replace all my n's by 3. So I'm going to get 1 plus 3x plus, and then it's going to be 3 minus 1 over 2. I'm going to put the factorial in just to remind myself. X squared plus 3 minus 1, 3 minus 2, all over 3 factorial x cubed, plus, we're going to be here a long time because this is an infinite series, 3 minus 1, 3 minus 2, 3 minus 3, all over 4 factorial x to the 4. But wait a minute, this 3 minus 0 is going to be 0, and any other term, all the other terms will have this in there. So we can still apply our binomial theorem to counting numbers, but what you'll find is when we go beyond the power of 3, if we've got a 3 here, then all the other terms are going to be 0. So this infinite series becomes just a normal series. So we don't have to worry about that. And actually this is now our binomial series. So I'm just going to tidy this up. This is going to become 1 plus 3x plus 3 times 2 over 2 factorial x squared plus 3 times 2 times 1 over 3 factorial x cubed. And I've done it in 2 different ways now. You might be confident and just go straight to this. If you realize that every time you do your binomial expansion, you just basically times by another number, but it's 1 less, and then you divide by a factorial that's 1 more every time, then you can actually do it a bit quicker. So I'm going to do that on subsequent examples to demonstrate a bit more clearly. But yes, be really careful if you want and put the brackets in, but sometimes I think actually it gets more complicated. If you can do it this way, then you can start seeing actually, look, these are cancelling out. 2 factorial is 2, it cancels out with 2. 3 times 2 times 1 is 3 factorial, so all of that is going to cancel out. And what I'm going to be left with is 1 plus 3x plus 3x squared plus x cubed. And that's our answer, and that's what we know from the binomial expansion, the previous version of it. So yeah, I think there's advantages to using the formula in the formula book, but there are also advantages to getting a really good understanding of it and doing it slightly quicker. Okay, example 2. Now I've got a 1 over, so how am I going to possibly do a binomial expansion for that? And what it does not mean is expand this into 1 plus 2x plus x squared and do 1 over that. That's not what we mean, because you've still got a reciprocal in there. So when you see this sort of thing, you have to realize that you need to write it in the binomial expansion form, 1 plus x to the n. That's in this case is going to be 1 plus x to the minus 2. Okay, so we've got our formula. So we've got our function. N is equal to minus 2. And let's have a go at using this sort of alternative version of using the binomial expansion. Nothing wrong with the first one, it's just this can become a bit quicker. So it's going to be 1 minus 2x. And then I'm going to add, right, this time I've got minus 2, but I'm going to multiply by minus 3 because it's 1 less, just like I was doing before here. It's minus 2 minus 1. I've just done it a little bit quicker. And then I'm going to divide by 2 factorial and put an x squared in there. And then I'm going to do the same again. It's going to be minus 2 times minus 3 times minus 4. I'm just doing an extra term, 1 less. Just like I did before up here with this extra term, but I'm doing it a little bit quicker. I'm now going to divide by 3 factorial because it's 1 more, and I'm going to put in an x cubed, and then I can stop. Okay, see how much quicker that is? And now I can start cancelling things out, and I can do it with a calculator or without a calculator, because I can see that this 2 is going to cancel with this 2. I've got a double negative, so I'm going to get a plus 3x squared. Here I've got a 3 factorial, so that is going to cancel out with the minus 2 times minus 3 because they'll be positive, and what we'll be left with is a negative 4. Okay, if you prefer to do it the old way that I showed in this first bit in blue, then that's absolutely fine, but be aware of this quicker method. I think if I was in an exam, I'd probably I'd just be super careful, to be honest, because you don't want to spend ages, and I just think when you get all these brackets, it's actually more likely that you'll make a mistake. So please try it my way as well. Okay, one more example. So, this is stepping up a bit. We've now got a fraction, and we've got not an x, but a 1 plus 3x. What do you think is going to happen if I don't have an x in there? I've got a 3x in there. Well, what happens is basically what happens when you use the original binomial expansion. all I'm going to do is replace all my x's in the binomial expansion with 3x, and then it's absolutely fine. Okay, I'm going to just bring this down, put it here so we can see it. Okay, maybe it's worth going a bit. Let's take it the slower way. Right. So we've got that n is equal to 3/2, and our x. This is sort of our x in the binomial expansion is now equal to 3x. These are little inverted commas, by the way. Okay, so 1 plus 3x to the 3/2 is going to equal 1 plus 3/2x, dealt with the first term, plus 3/2, and then I'm going to write in full now, 3/2 minus 1 over 2 factorial, and then instead of having x squared, I'm going to replace that by 3x all squared. Oof. Plus 3/2, 3/2 minus 1 over, oh, I've not multiplied by the next bit, 3/2 minus 2 divided by 3 factorial, 3x cubed. And we can stop then. By the way, I've just realized something. Apologies. I didn't say what values of x is this expansion valid. Sorry. Well, because I've got 1 plus x, the power of n, it's going to be this thing here. Okay, if I'm answering this question, it will be minus 1 less than x less than 1. Or you can write it more concisely as the modulus function, but I know we've not covered that yet. Okay, back to this example. All right, I'm now going to simplify it, and I'm going to basically turn it into what I would have done if I did it the quicker way. But I'm kind of glad in this case I took it a bit slower. Just trying to move it up the page, sorry. Okay, move up the page slightly. Right, let's carry on with this. So we're going to get it equals 1 plus 3/2 plus 3/2 times a half, okay, divided by 2 factorial times, actually, do you know what, as I'm doing this, I might as well start expanding this out. So this will actually be 9x squared. And then my last term will be plus 3/2 times a half times minus a half, all over 3 factorial. And now it's going to be 3x all cubed. That is going to be 27x cubed. Okay, hopefully this is making sense. Right, I'm actually going to delete this and move this up the page again. So if you're confident, this might be, I would like to see the 3x squared in there, but you could jump straight to this sort of thing. Okay, to be fair, this point is definitely calculator time. You can do it in your head, but you probably want to be careful. Do you know what? I'm going to do it in my head. I missed an x out there, didn't I? So it's going to be 1 plus 3/2x. Here I've got 3 times 9. That's going to be 27. And then I've got divided by 2, divided by 2, and divided by 2. So I'm going to be divided by 8. And then we've got my x squared. Here, what's going on? Well, this 3, I can cancel out the 3 with this 3, and I'll change that to a 2 because it's actually 3 factorial. I see I've got a negative in there, so it's going to be minus. So it's going to be minus, again, 27, but this time I'm going to be dividing by 16 because I'm dividing by 2 4 times. And then I'm going to have my x cubed in there. And after that point, it's going to alternate because I'm going to multiply by minus 3/2 next, and we come back to being a plus. That's what happens when you get a negative. So that's our answer. Right, for what values of x is this expansion valid? This is where it just gets a little bit trickier because it's the same as before, but now our x is actually 3x. So valid for minus 1 less than 3x less than 1, which means actually it's minus a third less than x less than a third. So this is actually my answer for where it's valid. Okay, good. So these are 3 examples. They've got increasingly more difficult of applying this new binomial expansion. It's the same kind of thing as your previous binomial expansion, but you need to be careful with negatives. You need to be careful with fractions. It's not quite as straightforward. I'm not saying the first one is straightforward, by the way, but it is more challenging to apply than the earlier binomial expansion. Be aware of the range that it's valid as well, and when you get a 3x, basically replace all your x's by 3x. Right, let's just see a minute these functions again. So back to the second example, which was 1 over 1 plus x squared. If I draw this function, then it looks like the function in black, and you might see that it's like 1 over x squared, but we've translated by 1 in the negative x direction. Now see what happens if we take the first 4 terms of our binomial expansion in red, then look how well it agrees between 1 and minus 1. Well, it agrees really well between minus a half and a half, I would say, pretty much spot on. But then it goes away and gets worse. And then once we've gone beyond 1, it is absolutely shambolic. It cannot possibly be the same thing. And that's because it's not within our range. Remember, we said it was true between minus 1 and 1, and it is completely wrong after that because the function goes to infinity. Now, if I add more terms, then it gets a bit better after a half. Why is that? Because technically I've truncated my expansion, haven't I, in my answer? And so I'm going to lose some accuracy. It's only equal if I've got an infinite series. So I've got to remember that I'm approximating this thing by a truncated series in these 2 cases. As I add more terms, it becomes better. But I'm going to need more and more and more terms to get it better for 1. Now, if you think about it, why is it really good for small values of x? Well, it's because if x is like 0.1, then x to the 9 is going to be insignificant. But if x is 0.9, then 0.9 to the power 9 is actually not that small. It's 0.4 nearly. So that's why it's better for small values of x, very small values of x, and for very small values of x, you can, it's almost a perfect fit. For larger values of x within the permitted range, you need more and more terms to get a better approximation. So that is just something to be aware of. Let's look at one more, the third example. So if we plot this function actually in black, here's what it looks like. Actually, the function is not defined if x is less than minus a third, because you're basically taking the square root of a negative number, so just be aware of that. We get really good fits between minus a third and plus a third. Because these terms kind of, again, they get small quite quickly for small values of x. Beyond a third, we see that actually, you can actually see it does it quite well up to 1 in this case, but as you add more and more terms, I would actually expect it to get worse. I'm not going to get any more into that, but basically I'm just trying to show you how good it can be at approximating when you take some of the terms and talking about this range of which it's true for and what will happen as you add more terms. Okay, good. We're going to do 3 more examples because we've seen how to do these general expansions, but there's lots of questions that are just slightly more awkward that I want you to see and us to discuss. So please, can you pause the video and have a go at each one, and then watch the solution, check or just skip through it and see if your answer is correct. There are some tricky bits to each of these questions. Okay, the first one, right. First of all, let's write just above the function what we are going to be doing. So this x that we're going to substitute into our binomial expansion in our case is actually minus 2x. That's the first thing to note. Be really careful. I need to include all of this. And then I've got that n is equal to a half in this case. So what I'm going to get is that 1 minus 2x to the half is going to equal, and now I'm going to use my binomial expansion, 1 plus a half. Okay, I've substituted in my n, and then I'm going to substitute in my x, it's minus 2x. And then it's going to be plus a half, and I'm going to do it my quick way now. I'm going to then times by minus a half, and divide by 2 factorial. And then it's going to become minus 2x squared. And then finally, I'm going to do plus a half times minus a half. I'm going to then minus 1 from minus a half, which is minus 1.5, or minus 3 over 2. Divide by 3 factorial and put minus 2x cubed in there. Okay, good first step. Equals, and now I'm going to start cancelling things down. You might want to use a calculator for this. I'm going to do it without. So the half is going to cancel with the 2, and I'm going to be left with 1 minus x. This thing here is going to become 4x squared when I expand the bracket. And the 4 is going to cancel with that half and that half. And I'm going to be left with a minus and a divided by 2 factorial. So it's going to be minus a half x squared. And then over here, this is going to become minus 8x cubed. These two negatives are going to cancel, but I've still got one negative left over. The 3 factorial I can write as 3 times 2, and I can cancel that 3 out with that 3. The 8 is going to cancel with the halves, these halves here. So I'm left with a negative, and I'm dividing by 2 again. This is actually going to become minus a half x cubed. And I have my binomial expansion. Right, I've done it up to the term in x cubed. It's not asked me for the range of values. Do you know what? I just think it's a good habit just to write them down. So in this case, I know there's a minus there, but it's still minus 1 less than 2x less than 1, and so it's minus a half is less than x less than a half. Now, how are we going to choose a suitable value of x to find an approximation for root 2? I want you to think about this, pause the video and have a think about what value of x could help you out. Okay, I'm going to talk this through. One value of x, which might seem like a good idea, is a half, minus a half, because if you put in minus a half as x, you actually get 2 inside the bracket itself, so you would get the approximation. The issue is that, first of all, x is not small enough. Okay, we know that approximation gets better the smaller x is. I've been showing that on the graphs, and actually in this case, minus a half is on the borderline. So we can't use this. It's not going to be very good. My second option for you is 0.01. Note this is not obvious at all the first time you see it, but we're going to talk about why. Right. Before we substitute in 0.01, let's see what happens. X equals 0.01 implies 1 minus 2x to the half is equal. Now when I substitute that in, this is going to be 0.02, and so I'm going to get 0.98. And then I'm square rooting it, I'm raising it to the power of half. Okay, now why is that useful? Because I can write this, I somehow want 2 by itself. Okay, now what do I multiply 2 by to give me 0.98? Well, it's 2 times 0.49. And this is the key bit. I can then write this as root 0.49 times root 2. And this is like a square number in some sense. It's not a square number because it's not a whole number. But the square root of 49 is 7. Square root of 0.49 is 0.7. So Doing it this way means that I've chosen a really small value of x. Okay, that's the advantage. It's going to be accurate. And I've managed to get it, so I've got root 2 by itself. This is only going to work for some values of x, and it's hard to be able to spot that. But yeah, technically you might need to spot it. So therefore, root 2 is going to equal, and now I'm going to substitute my value, my 0.01 in, 1 minus 0.01 minus a half times 0.01 squared minus a half times 0.01 cubed, and I need to then divide by 0.7. Okay, this is definitely calculator time. Let's get the fraction button up and let's write this in. 1, sorry, I'm just trying to fit everything on, minus 0.01 minus, instead of a half, I'm going to write 0.5, it's just quicker, times 0.01 squared minus 0.5 half again, times 0.01 cubed, press down, 0.7, please work, 1.41421. That is pretty good, I'd say. We can actually, let me just write this down. So what did it say? Find an approximation. So it doesn't have, I've made this question up. You'd probably say to 3 significant figures or something like that. 1.4142. 1.4142. By the way, to do the percentage error, we would actually find the difference between our answer and the real answer. So if we subtract the square root of 2, then I get this number here. It's positive. Look how small that is. So our answer was actually accurate up to like 8 decimal places or something like that. So I found the difference. If I now divide by the true value, which is root 2, okay, and then times by 100, that tells me the percentage error. And that is, look at that, that is the percentage error. We've managed to use binomial expansion to get such an accurate value for root 2. It's ridiculous. And you got to think about this. When people didn't have calculators, they might have an abacus or something like that. They could make really accurate values for square roots using this theorem. The tricky bit is having to divide by 7 essentially at the end, but that's not too bad. So you might be interested in just trying to do some more binomial approximations to things like the square roots. I might be testing you on that. So have a look.